Greetings and very good evening, children. Today we are going to see an interesting chapter. And though the chapter is very small, it has a lot of concept, and it's quite interesting for you to explore many things. But it is a comparative learning with the electrostatic as well. So to start with, I just wanted to get an answer from you. What is electric flux, children? You've already learnt. So what is electric flux? What do you mean by electric flux, children? You all know that? Electric flux is what? It is the total number of electric field lines passing through a closed surface. Is that? So let me repeat. Total number of electric field lines. Prior knowledge. So prior knowledge. Electric field lines. Total number of electric flux passing through a closed surface. So that is nothing but this is a closed surface. This is the area vector, let us suppose. So this is the electric field or area vector like that. And this is electric field. So you can say that electric flux is nothing but E dot A or EDS cos theta. That is electric field lines. All about static charge you learned. Got it? Same thing here, magnetic flux. Magnetic flux. What is magnetic flux? Lesson 5 magnetism lesson you have learned? No. Same thing. Here, total number of magnetic field lines. Total number of magnetic field lines. Field lines passing through the closed area. Passing through closed area or closed loop. Closed area or loop. Same thing, magnetic flux 5 is equal to B dot A, which is nothing but BA cos theta. So now this is the loop, this is area vector, and this is B. So you can say that theta over here. So B dot A, BA cos theta. Now, here, this lesson, we are going to use magnetic flux. But then we are going to produce some current. How is it going to produce current? Let us see here. Now this is the coil, children. This is a coil. I have taken a coil, conducting coil. For example, copper coil. I have taken a copper coil. I am going to connect it to a bulb. You tell me, children, whether the bulb glows now. You may be asking me, how come is it bulb glowing? Bulb won't even glow. Because there is no power source, there is no battery, there is no AC source, nothing. How come the bulb glows? Bulb doesn't even glow. Bulb won't glow because there is no source. No source. No source of power. So bulb won't be glowing. Now, a magnet, I am placing it. When I place the magnet, again I am testing it. Again I am testing it. Does the bulb glow? The magnet is at rest. The magnet is at rest. Now you tell me, when the magnet is at rest, will the bulb glow? No bulb glows. No, bulb won't glow. Bulb won't glow. Why does the bulb not glowing? Again the same reason. What is that? Again, no power source. No source of power. Since no source of power, no bulb glows. Now, all this we explored. But then you know that the scientist called Faraday. So he wanted to explore many things. So innovative things. So he was actually doing many experiments at the lab. And fortunately, one day what will happen, luckily, when he was meddling with the apparatus, he was able to see the glowing of the bulb when the magnet was brought into the coil. When the magnet was brought into the coil, is so amazing, astonished that there was a spark produced in the bulb. The bulb started what? Glowing. The flickering like that. When the magnet was brought in, it was glowing. Brought out, it was glowing. The magnet is stationary, it was not glowing. So from this, he was able to understand, oh, something is produced over there. So later on, he found out how come the current is produced. So here, Whenever the bulb is connected to a coil and the magnet is kept stationary, there is no glowing of bulb. There is no power. But then the same magnet, when it is brought into the coil or away from the coil, he found that the bulb was started glowing, which shows that current is induced. Current is produced. How come the current is not produced when the magnet is at rest? The magnet is at rest, the number of field lines passing through it remains constant. Whereas when the magnet is moved, what will happen? The number of magnetic field lines passing through the coil time to time changes. So therefore, you can say that the magnetic field lines, you can say magnetic field lines passing through the area time to time changes. Passing through this area. Passing through this area, time to time changes. Time to time changes. Or you can simply say that magnetic flux changes. Whenever there is a change in the magnetic flux, what is produced? Induced current is produced. That is why the bulb glows. Induced current is produced. Induced current is produced. Hence, what happens? Bulb is glowing. You can ask me, wonder, how is that possible? Very simple concept, insight, let me tell you. Whenever you are bringing the magnet into the coil, so this is the coil, I am taking the coil, I am bringing the magnet into the coil, this is the north pole. When you bring the magnet into the coil, the magnetic field lines are there, no? Changes, right? Time to time changes inside the coil, no? So therefore, this is a conductor, right? Please understand, this is a conductor. While it is traveling inside, what will happen? It creates an electric field around it. What field? The electric field around it. What type of field? Non-conservative field. Pushes the electron, pushes the charges. Where is the charge? In a conductor. So the charges are pushed to move from one end to the other end. So therefore, it produces a current that is called as what? Induced current. What a fantastic concept, you know that. You have to enjoy and learn. So whenever you bring the magnet inside, the time to time there is a change in the magnetic field. So that magnetic field produces an electric field around it. Where? Around it means in the loop that pushes the charges to move from one end to the other. Where is the charge present? Charge is present in the conductor, in the loop. So therefore, it moves from one end to the other end. Therefore, the potential is created. Hence, current is produced. That current, you call it as what current? Induced current. Therefore, this lesson is called as electromagnetic induction. Induced electricity due to change in magnetic flux. That's all, children. The whole lesson got over. This is the essence of outsketch of borderline of this entire lesson. Electromagnetic induction. Current is produced, electricity is induced due to change in magnetic flux. So, who is the root cause? Who is going to be the father of this investigation or discovery is none other than Faraday. We'll see that. Now, I have already told you about magnetic flux. The same thing here. Magnetic flux through surface is the number of magnetic field lines of force passing normally through it. So, the number of magnetic field line passing normally through it in a closed surface, closed area, normal to this area. So, magnetic flux is a scalar quantity like the electric flux. Flux phi is equal to BA cos theta, or you can write it as B dot A. SI unit of magnetic flux is Weber. You can simply write it as Weber WB. Or you can write it as Tesla meter square. That you don't need to know. Just we will always use Weber only. But then there is another unit Tesla meter square that you can just get to know. Right? So now positive flux when theta is equal to 0 to 90 degree. Or theta is between 270 to 360 degree. 0 flux 90 degree and 270 degree. Negative flux 90 degree to 270, for example 190 degree. So there is the three types of flux. So of course we know that flux phi is equal to BA cos theta. I have already told you if there is a change in flux, induced current is produced. What are the ways of changing flux? Number 1, changing B. Number 2, changing area. Number 3, changing theta. See, change in B, change in strength of the magnetic field. Changing area of cross section of the coil. Changing theta, orientation of the coil at the magnetic field. Any of the combination of the above produces an induced EMF. Got it, children? So now we are straight away going to Faraday's first experiment. What is it Faraday first experiment says? I've already told you one coil I've taken. A magnet is brought into the coil or away from the coil, put inside, put it outside, forced to push inside and bring it outside. Suddenly or quick by bringing it in or out, there is a change in the flux. Time to time, there is a change in the flux. Therefore, induced current is produced. That is first law. You can see here. So the coil north is brought in. So therefore, current is produced. Similarly, here south is brought outside, current is produced like that. So when it is stationary, there won't be any current. Only if there is a relative motion, there is a current. So therefore, Faraday first law, what you can write here, relative motion between. You have to write like relative motion between the coil and the magnet. Coil and the magnet produces a change in magnetic flux. This is a very important keyword, children. Produces a change in magnetic flux. Produces a change in magnetic flux, and hence induced EMF is produced. Induced EMF or current is produced. Current is produced. This is Faraday's first law. Similarly, Faraday's second law will go. Faraday's second law. Second law. Faraday's second law. What is this Faraday's second law? First law, only one coil I've taken. Now this is second coil. So I'm taking second coil. I'm going to pass AC current. AC current, alternating current. And primary coil, time to time there is a variation in the current because AC current. Secondary coil, which is placed coaxially, there is no power source. But even though there is no power source, the current is going to be produced. How is that possible? Because time to time there is a variation in the current. Whenever there is a time to time variation in the current carrying coil produces magnetic field around it, which you have already learned. Did we learn or not? When you pass current through the coil, what will be produced? Solenoid. Can you recollect fourth lesson? When you pass current through the coil, inside a solenoid, magnetic field is produced. Same way, when you pass current through the coil, magnetic field is produced in the coil. But here, what type of current you are passing? Varying current. So whatever the magnetic field lines changes, whatever the magnetic flux changes in P coil, there will also be a change in Q coil because the two coils are placed coaxially parallel to each other. And magnetic field line form closed loop only, which you have learned in lesson 5. So therefore, it has to pass through the secondary coil and forms a closed loop. So therefore, time to time there is a change in the flux. Hence, there is also a change in the flux in the secondary coil, due to which induced current is produced. Where is the induced current produced? Induced current is produced in the secondary coil. So galvanometer deflects like that, either towards left or towards right. Left and right, it will be keep on changing as because of the changing current. So therefore, Faraday's second law, what does it say? Faraday's second law, what does it say? States that induced EMF in the secondary coil, secondary means yes, secondary coil, is directly proportional to rate of change of flux in the primary coil, d phi by dt. That is all, children. Taking out the proportionality by constant E is equal to constant K is equal to 1 d phi by dt. Magnitude of the induced EMF, therefore I put mod. That is all. First law, you move the magnet into the coil or away from the coil, there is a change in flux, hence induced EMF is produced. Second law, whenever there is a change in flux in the primary coil, how do you change the flux? Whenever there is a varying current flowing through the primary coil. Doesn't mean that only AC current. You can also do like, see, I am just passing DC current momentarily with the help of the switch. I am pressing the key or removing the key. This is called tap key. So when you use tap key, momentarily there is a variation in the current. Momentarily there is a variation in the current. Whenever there is a varying current, momentarily also there will be a flux changes, due to which induced current is produced in the secondary coil. So either this or that. So induced EMF is directly proportional to, if that is second law, that's all. Right? So now next come, very important concept. Second law over. I have already told you, rate of change of magnetic flux linked with the primary coil produces induced EMF in the secondary coil. E is directly proportional to d phi by dt. So we have seen that. The next, how to find out the direction of the induced current. Other we are going to see. Okay, how to find the direction of the induced current. So that is called as Lenz's law. How to find out the direction of the induced current was given by Lenz's law. Such a very important concept, children. How to find the direction of, how to find the direction of induced EMF. Direction of induced EMF. Induced EMF or current in the loop. I have already told you induced current will be produced only in the loop, nothing else. Because you have to allow the charges to flow. You have to create an electric field. So magnetic field lines will pass through the closed loop. So there will be a creation of electric field, that is non-conservative field, which forces the charges to move. So how to find the direction of induced current in the loop or conducting loop? Conducting loop. You have to see that. How to find Lenz's law? Lenz's law states that the direction of induced EMF, direction of induced EMF produced in the coil is always in such a way that it opposes the cause of change in magnetic flux. Opposes the cause of change in magnetic flux. Cause of change in magnetic flux. Opposes the cause of change in magnetic flux. One example let me give you. Now this is a magnet, north south, and this is placing a coil over here. Now your magnet is brought in. You are bringing the magnet. When you bring the magnet, the coil has the tendency to oppose. That is what Lenz's law states. What does it say? The direction of the induced EMF produced in a coil is always such a way that opposes. See, when you bring the magnet inside, right? When you bring the magnet inside, flux, what happens? Flux increases. How do you know flux increases? When the magnet is outside, only two lines are passing. Same magnet, if it is brought inside, how many field lines will pass? Many field lines will pass. So therefore, you can say that flux increases. Due to increase in flux, what will happen? It forced to produce an induced EMF. An electric field is created. Induced EMF is produced. The flux always says that it is opposes. Can you check here? It opposes the cause of change in flux. What is the cause of change in flux here? What is the cause? Why the current is produced here? Tell me. Why the current is produced? As because you move the magnet. Okay, tell me, when the magnet is stationary, is the current produced? No. You are moving the magnet is a cause. Cause. C-A-U-S-E, cause. Moving the magnet. Where are you moving the magnet? Moving the magnet into the coil. Into the coil. Moving the magnet into the coil is the cause. Okay, what is the effect? Effect is nothing but production of induced current. Production of induced current or induced EMF. Where is the production of induced EMF or current? In the coil. So it opposes the cause. The current opposes the current produced. Current produced. Which current? Induced current produced opposes the cause. Opposes the cause means what? Does not allow it to come inside. It is coming inside. So therefore I have to write does not allow it to come inside. Does not allow the magnet to come inside. Magnet to come inside. Rather, you can say that does not allow the magnet to come inside, right? So what does it do rather? That is, it pushes it back. Pushes means repels. That is, it repels back. Repels it away. Repels it away means, therefore, it attains what polarity? It attains, pushes it, repels. Repels means what polarity it has to attain, you tell me. It has to attain, no, some polarity. What polarity it has to attain? The coil attains North pole, then only what happens? Ripple, right? It has to ripple. So therefore you can say the coil attains north pole. If it is north pole, then what is the direction of the current? According to, if it is north pole, what is the direction of the current? So we'll see that. According to N rule, this is also one rule you have to know. According to N rule, if the coil observer, for an observer, the coil says that if it is north pole means it must be, the current in this is going to be anti-clockwise direction. For an observer, current direction is going to be anti-clockwise direction. North pole means anti-clockwise. According to N rule, for an observer looking at the coil, if it is north pole, take it as anti-clockwise. Okay, what if it is going to be south pole? If it is going to be south pole, then you have to take it as what? Clockwise. If it is going to be south pole, then you have to take it as clockwise. For an observer's eye, if it is going to be south pole, you have to take it as clockwise. This is called as N rule. Please understand, children. Once again, let me repeat the concept here. What does it say? You are finding out the direction of the induced current. Already we know that there is a change in flux. That is what? Induced EMF. Now we got to know there is going to be a change in flux whenever you are bringing the magnet into the coil. When you bring the magnet into the coil, what does this Lenz's law states? Lenz's law states that when the magnet is brought inside or outside, there is a change in magnetic flux. It opposes the cause of change in magnetic flux. See here, read out. All of you read out the direction of the induced EMF or direction of the induced current such that it opposes the change that is producing it. I've already told you what is the change here. What is the cause of the change here? We have seen no here. What is the cause? Moving the magnet into the coil is a cause. What is the effect? Production of induced current is the effect. The induced current produces opposes the cause. That means does not allow it to move inside. Does not allow it to move inside means what does it do? Pushes. Pushes means repel strongly. While it is repelling, what polarity it has to attain? North. North means anti-clockwise. So therefore, it produces anti-clockwise direction of the current. Since it is anti-clockwise, the galvanometer deflects anti-clockwise. That's all, children. Right? So this is always it opposes. So one more example, let me just give you. One more example I'm going to give you. See here, this is the coil. I'm going to bring in south pole as brought away. What is the deflection of the galvanometer? I'm bringing this magnet brought out suddenly. When you are bringing out suddenly, what happened? The coil has the tendency to oppose. Coil has the tendency to oppose. What is that, children? Tendency to oppose means what does it do? Does not allow it to go away. Does not allow it to go away. So since it is not allowing it to go away, what does it do? It pulls it towards. Since it is pulling it towards it, what happened? You can say that it is attracts. Since it is attracting, what is the polarity it attains, children? Attracts. If it is going away, so it has to attract, no? Since it is attracting, so therefore it has to attain what pole? North pole. Again, for north pole, for an observer's eye, if it is going to be north pole, what wise, children? Anti-clockwise. So therefore, current in the coil is anti-clockwise. Therefore, the galvanometer deflects like that. Do you understand? Okay, third, what if it is going to be in this direction? You tell me this is the coil. There is another coil here. Galvanometer. Here also galvanometer. This is the magnet. North pole, south pole. I am bringing it inside like that. Can you check here, children? It's very easy, children. You can do it. Tell me now. This is coil P. This is coil Q. Very easy. For coil P, for an observer from magnet end, I am going to look at. I'm going to look at from the magnet end. So therefore, I am putting an I here. So now when the magnet is brought in, the coil has a tendency oppose. Oppose means what polarity it attains? Oppose means does not allow it to come inside. So therefore repels. For repelling, it has to acquire north pole. So it is moving away. Since it is moving away, does not allow it to move away. So attract. Since it is attracting, what polarity it attains? North pole. North pole means what wise? Anti-clockwise. So here also oppose north pole means what wise? Anti-clockwise. So therefore, the galvanometer deflects like that. So here also the galvanometer deflects like this. Can you check here? Both ends anti-clockwise. Very easy. This is Lenz's law. So based on Lenz's law, we're going to have to see here question number 1. This is the NCERT question. You tell me now, you have to see the winding of the coil properly. Okay, children? Now look at that. South pole is brought in. Since the south pole is brought in, what is the direction of the, here what polarity it attains? The coil has a tendency to oppose. Since it is opposing, here also south pole. South pole means what wise? Clockwise. You see that. See properly here. You can see here. Enlarge it, magnify it, so that you can get an idea. Okay, I enlarged it. So now this is south pole here. Why south pole? Because it does not allow it to come inside, repel, opposes. Do you understand, children? Still, if you have any doubt, you ask me. Coil, when it is magnet is coming inside, pushes it away. When the magnet is going away, pull it towards. Both the cases oppose. South pole. South pole means what? For an observer's eye, if it is going to be south pole, then I have to take it as what? Clockwise. So here also clockwise. Clock. How does it go? Clock in your house. In your house, does the clock goes from 12 to 3 or 12 to 9? 12 to 3. So clockwise. Is it clockwise? Yes. Since it is clockwise, you can see here, update, just draw like that and then go like this. Do you understand, children? How is it going? QRP. Is it going like that? QRP. Is that no? Right? So QRP. So answer is QRP. Q to R, R to P. Do you get it, children? Likewise, look at the second one. The second one is same as that of the first one, I guess. Yeah, so second one is first one. So now let us go to the next one. Okay, now children, listen. 2 coils now. This is also based on the Lenz's law. When the tap key is closed, you can check here. Yeah, let me magnify it. Okay, children, tap key is pressed, closed, means what? Current, what happens? Key is pressed, momentarily there is an increase in current. Quick, I have to do it, children. No minute time. Increase in current. When there is an increase in current, flux, what happens? Increases. Now you have to use right hand thumb rule. What rule you have to use? Right-handed thumb rule. In the right-handed thumb rule, thumb represent the direction of magnetic field and the fingers encircling will give you the direction of induced current. So now here, in this case, I can say here this is magnetic field. Sorry, this is induced current. Induced current. And thumb represent the direction of magnetic field. Okay, children, here you can see here first case, what are you supposed to find out? So let me just make you understand, then I'll come back here. So listen, children. So this is how to use the right hand thumb rule. Right-handed thumb rule. I'm not going to use the right-handed Fleming's right hand rule. I'm going to teach you right-handed thumb rule, accelerator rule. Okay, how to find out? Let me teach you. Please listen carefully. We all know that for a linear closed conductor, closed loop, closed current carrying loop, closed current loop. Thumb is the closed current loop. Thumb is the magnetic field and fingers are the current. Am I right or not? We already found out, right? Already know that, right? We learnt in 4th lesson. Same thing. For a current loop, closed current loop, I have taken a current loop like that. For a closed current loop, thumb is the magnetic field. Thumb is the magnetic field. And fingers represent the current. That is for the closed current loop. If I say current is in the anti-clockwise direction, then my thumb represent what? The magnetic field. Do you get it? Do you understand? Same thing here. For the loop, induced current, you have to find out, no. For induced current, same formula. For induced current, how to find out the induced current? Please listen carefully. We know that according to Lenz's law, by Lenz's law, induced EMF is always in such a way that opposes the cause of change in flux. So E is equal to minus d phi by dt. Hereafter, Lenz's law, Faraday's law and Lenz's law together. Faraday's law is to find the magnetic flux magnitude with respect to time. So Faraday's law is for induced EMF magnitude, whereas Lenz's law to find out the direction. So E is equal to minus d phi by dt. Minus sign denotes that direction of the induced EMF is opposite to the cause of change in flux. So I can write minus sign denotes minus sign denotes direction of the induced EMF, denotes direction of induced EMF, direction of induced EMF is opposite to the cause of change in magnetic flux, opposite to cause of change in magnetic flux, change in magnetic flux. That is why minus sign here. For n turns, you can write minus n into d phi by dt for n turns. So E is equal to minus n into d phi by dt, or you can write it as minus n into phi 2 minus phi 1 divided by T2 minus T1. If phi 2 is greater than phi 1, that is nothing but increased flux. Increased flux. Flux is increased. Then EMF is negative. If phi 2 is less than phi 1, that is nothing but decreased electric flux. Decreased magnetic flux. Decreased magnetic flux. Decreased magnetic flux. Then you can say that induced EMF is equal to what? Positive. This is a tactics and technique going to find out. So hence I am going to use the right hand. Right hand what rule? Thumb rule I am going to use. So same thing here, I am using right hand thumb rule. For example, I am going to take a loop. In this loop, current flows in the clockwise direction. Clockwise direction. There is another loop inside. What is the direction of the induced current in the B loop? You can say very well, no induced current in the B loop. Can you guess and tell me why no induced current in the B loop? Induced current, no induced current in loop B. Why? Why children? Why? Yes, because what current here? Constant current. If the current is constant, magnetic flux is not changing. No change in flux. No change in magnetic flux. So therefore, no current. No induced current. Now, at the same time, I am modifying the circuit. Check here. Very simple way I am modifying the circuit. I am using the tap key and then I am passing the current. Tap key, switch. Momentarily, I am going to tap it. So when you momentarily you tap it, there is a current flowing in this. When the current is flowing, there is a possibility for the induced current in this B coil. How? First, you have to find out magnetic field direction. B direction. Where are you going to find out B direction? B direction for coil B. For coil B. Next, number 2. Find flux whether it is increasing or decreasing. flux increasing or decreasing? I have to find out. I have to find out whether flux is increasing or decreasing. Third, you have to find out the direction of the induced current. Direction of induced current. Come on, children, it is very simple for you to learn. Come on. Direction of induced current. How to find out the direction of magnetic field? I have already told you, right hand thumb rule, right? Actually speaking, Lenz's law, what does it say? Whenever there is a increase in flux, the coil does not allow it to support increasing flux. It decreases the flux. Whenever there is a decrease in flux, the coil does not allow it to decrease the flux, whereas it increases the flux. All that need not find out. There is a tactics which I am showing, helping you to find out the direction. First and foremost thing, find the direction of the magnetic field for the coil B. How does the coil present? Both the coils are placed coaxially. How do you say coaxially? Because centers are coinciding like that. Centers are coinciding like this. Can you see here? Yes. Whatever the magnetic field for the first coil, the same thing is applicable for the second coil. Let me repeat. Coaxially placed. Either it is placed like this or placed like this. Coaxially placed. But one is like this, another is like this, is not coaxial. Coaxial means centers should coincide. You can assume like this or you can say like this. So coaxially placed, whatever be the magnetic field for the first coil, same thing is applicable for the second coil. So what is the magnetic field direction for the outer coil according to right and thumb rule? You tell me. According to right and thumb rule, the magnetic field for the center of the first coil, A coil, is inwards. So here it is inwards. Magnetic field is inwards over here. Same thing for the B coil, it is inwards. So I have to say inwards, perpendicular into the plane. Again use right hand thumb rule. I am going to use right hand thumb rule because secondary coil is also closed coil. Listen very carefully. You have to listen very carefully. The concept is very important. If you know this concept, you can proceed further. First, what are you finding out? Magnetic field. Into the plane of the paper, I put it into the plane of the paper. Now, second coil, also a closed coil. What is the direction I am getting? Clockwise I am getting. But then, flux is increasing. Since it is increasing over here, how do you know flux is increasing? Because switch is pressed. Tap key. Switch is pressed. Flux is increasing. Whatever the direction you are getting in your hand, I am getting clockwise. Why? Because magnetic field is inverse. Why magnetic field is inverse? Because outer coil current is clockwise, the magnetic field is inverse. So magnetic field is inverse. Flux is increasing. Whatever I am getting, put it opposite. I am getting clockwise. Put it opposite. Therefore, the answer for this is anti-clockwise direction. What is that? Anti-clockwise direction of the current. So current flows in the anti-clockwise direction. That's it. Current flows in anti-clockwise direction. This is called as Fleming's right hand thumb rule. You can use screw rule or thumb rule like that. Traditional way of using is right-handed Fleming's right hand rule. That we are not using it. You can use this screw rule or right hand thumb rule like that. So for any conductor, it is always like that. One more example I am going to give you. Now listen here. This is the coil. The coil here, I am going to pass a current. You can see here, switch is removed. Actually, switch is present. I am going to remove the switch. Remove the switch momentarily. Remove the switch momentarily. When the switch is released, what is the direction of the induced current in the secondary coil? Other question. I have already told you whenever there is a change in flux in the primary coil, there will also be a change in flux in the secondary coil. So now, first of all, let us find out B direction. Direction of B. We have to find out direction of B. In what coil? Secondary coil. B in secondary, you find out. Magnetic flux increasing or decreasing, find out. Flux increasing or decreasing. Or decreasing, you find out. Then you have to find out the direction of what? Induced current. In the board examination, nobody will ask how do you get it. But you have to know, right? Induced current. Direction of induced current. These three things you have to know. First, this is the coil. Originally, how is the current flowing? Current is flowing in what direction? Clockwise direction. When the current is flowing in clock, there are two ways. Either use right hand thumb rule and find out, or you can use magnet rule. So now current is clockwise, so therefore this is south pole, this is north pole. Another coil, so therefore the current, the magnetic field lines flow from north to south, like that. But the next coil has a tendency to oppose, right? So therefore this produces what? North pole. Ripples. So since it is producing north pole, so it should be anti-clockwise direction. That is one way. I don't want all this way. Immediately, easily I have to find out by using right hand thumb rule. Yes, you can find out. Now, number one, what is the direction of current in the primary coil? Tell me. By looking at the coil, you can say it is clockwise. Since it is clockwise, what is the direction of the magnetic field? You see like this. Magnetic field. I am keeping the coil like this. Coil is going like this. This is my eye. Observer is here. I am looking at the coil here. So, clockwise. Since it is clockwise here, magnetic field is inwards. So, here magnetic field is going inwards. So, here also magnetic field is going inwards. Understood? I told you, no. Whatever be the magnetic field for the first coil, same is applicable for the second coil, because both are same axis. Since the magnetic field is inwards, what is the current in the secondary coil? What is the current according to right hand thumb rule? Here also inwards, because the observer is in the side. Observer is looking at the coil three-dimensionally. So current is clockwise. So therefore magnetic field is inwards. Here also inwards. So current here it has to be clockwise. Since the flux is increasing over here, whatever I am getting, put it opposite. Therefore I should put anti-clockwise. Since it is anti-clockwise, so therefore what should I do? What should I do? I have to put, do not say anti-clockwise. The galvanometer deflects in such a way that it is moved from X to Y. Don't say anti-clockwise, should say X to Y, not Y to X. So current direction is going to be X to Y like that. Do you understand? There is another type which quickly let me tell you. Find direction of the current. Find direction of current. Direction of induced current. Induced current in the loop. The loop A. This is other type, children. You know magnet type. You know the secondary two coils type. Now it is induced current in the loop. This is current direction, straight wire. Straight wire current is decreasing. Oh, the previously I have taken what? Remove the key I have taken, right? I'm sorry. I have removed the key, right? When you removed the key, what happens? Flux, what happened? Decreasing. When you remove the key, right? Flux is not increasing. When you withdraw the key, what happened to the current? Decreases. So flux decreases. When the flux is decreasing, whatever the direction you are getting, appadiye you put it. Do not change. So magnetic field is into here. You can see here magnetic field. Here you can see, no, magnetic field. So the magnetic field is into, right? So magnetic field inwards. See here inwards. Inwards. Look at the coil. It is inwards. So magnetic field is inwards. So therefore, since it is inwards, current is clockwise. So I put clockwise here. Since it is clockwise, do not write clockwise. Instead of writing clockwise, what are you supposed to write? You have to say current will flow from Y to X. Current will flow from, induced current will flow from what? Y to X. Hope you understand, children. Next, quickly let us see that this straight wire I decreases. This is the loop A. What is the direction of the same procedure? First find B direction, magnetic field direction, direction of B. Where are you supposed to find out direction of B? Direction of B in the loop. Next find flux, increasing or decreasing. Flux increasing or decreasing. Next, what do you find out? What are you supposed to find out? Direction of the induced current. Direction of induced current. So now you tell me what is the direction of B in the loop. How to find out? Use right hand thumb rule, that's all. 2 times you have to use, children. You have to be very clever to switch. Only switching. Linear conductor, which is the current, which is the magnetic field. This is thumb is the current, fingers are the magnetic field. Linear conductor. Linear conductor, thumb is the current. Please listen carefully, tap your brain. Linear conductor, what is the current? Thumb is the current, fingers are the magnetic field. Whereas circular loop, just opposite. Fingers are the current, thumb is the magnetic field. Fingers are the current, thumb is the magnetic field. So now I curl in fingers in such a way that the magnetic field above the wire I want. I don't want below the wire. Why? Because the loop is above. So above the wire, so here above the wire, how is that magnetic field? Look at that. Is it coming outwards? Is it coming outside the board? The board is here, it is coming outside the board. So therefore, you can say outwards. The magnetic field is outwards. Now switch. Use the right and thumb rule. Magnetic field inwards means I have to keep it like this. Inwards. Inwards means keep it like this. For your board or for your paper. This is your paper. Inwards means how do you keep? Like this. But here magnetic field is outwards. See how am I keeping outwards? This is outwards. What wise I am getting? Check. Anti-clockwise. Do I need to change? Don't change. Why? Because the flux is what happened? Decreases. How do you know flux decreases? Because it's given here, current is decreasing. Therefore, flux decreases. Since the flux is decreasing, whatever the direction you are getting, keep it as such. So, I am getting anti-clockwise. So, therefore, I have to write it as anti-clockwise direction. Do you get it, children? Likewise, one more I'm going to give you. Come on, quick. You know it. You know it. This is current direction. Now, this is loop A. The loop A is brought towards the wire. Suddenly brought towards the wire. So, answer. I'm going to give you an answer. So, here in this case, use right hand thumb rule. Now, what are you supposed to find out? Even though you're using right hand thumb rule, what are you supposed first to find B? Find direction of B. In loop A. The loop A, what is the direction of B, children? Quickly tell me. Guess. Current is, thumb is the current, fingers are the magnetic field, linear conductor. So fingers are the magnetic field. Look at that current direction, upwards. So where is the fingers going? It is going inwards. My paper, it is going inwards. So under loop A, magnetic field is inwards. So I put magnetic field inwards. Flux, what happened? As because you are bringing the loop inwards, you are bringing it towards the wire. So therefore, flux, what happened? Increases. Therefore, what is the direction of induced current? Induced current direction is magnetic field is update switch. Use the right hand thumb rule again. When you are using it right now, which is the current? Tell me. Which is the current when you are using it? Correct. Fingers are the current, thumb is the magnetic field. So magnetic field is inwards and my fingers represent the current, that is clockwise. Since the flux is increasing, anti-clockwise. Hope you understand this. To get it, the last one more question here. This is a loop. Okay. In this loop, another loop is there. This is placed coaxially. This is secondary loop. This is primary loop. In the secondary loop, primary loop, there is a current flowing clockwise. What current? Varying current. Clockwise, okay, I will change it like this. Yeah. Switch is pressed. Yes is pressed. So, now you tell me yes is pressed. No. Current is what happened? Current is clockwise because current always flow from positive of the battery to negative of the battery. So now, therefore, what is the direction of the induced current in this? Here it is inwards. Here also it is inwards. So I have to get clockwise since flux is increasing. Flux is increasing. How do you know flux is increasing? Because switch is pressed, current is increasing. So therefore, flux increasing. Whatever I am getting, put it opposite. So anti-clockwise. If now you tell me this is the current, this is the loop. What is the direction of the induced current? This is the loop A. Okay. Now current I increasing. It is actually a Hart's question. This is current carrying conductor. Now for this current carrying conductor, where is the magnetic field? You tell me. Magnetic field will be around the current carrying conductor. So I am drawing the magnetic field lines. See here, I am drawing the magnetic field lines. For the loop, where is the area vector? The loop is there, no? The loop, where is the area vector? Area vector means normal. Normal is upwards. So therefore, let me draw normal is upwards, n cap. This is magnetic field. What is angle between B and A? Angle between B is perpendicular to area. So therefore, magnetic flux phi is equal to BA cos theta. So therefore, flux is equal to 0. Therefore, no induced current. Do you get it, children? That is all very easy. Now, you tell me what is this direction? This is slightly different. Can you check here slightly different? Let me enlarge. You can check here. This is a rheostat. The number of turns is there. No, that has been decreased. You can check here. The number of turns is decreased. Number of turns is decreased. When the number of turns is decreased, length of the wire is decreased. Length is decreased. When the length decreases, R is equal to rho L by A. What happened to resistance? Therefore, resistance decreases. Now you tell me, when the resistance decreases, therefore what happened to current? What happened to current according to Ohm's law? Current increases. When current increases, flux, what happened? Increases. When the flux is increases, what is the direction of the induced current here? Current flows from positive to negative, so current is flowing in the anti-clockwise direction. First coil anti-clockwise. Keep it like that. The first coil anti-clockwise. The first coil is there, no, anti-clockwise. When it is anti-clockwise, what is the direction of the magnetic field? Magnetic field is towards positive x-axis. What is the direction of the magnetic field in the secondary coil? That is also towards positive x-axis. I have already told you this always opposes the magnetic flux. So magnetic flux is increasing. But the secondary coil opposes the increase in magnetic flux. That means it has to decrease. It produces the magnetic flux in the opposite direction, hence induced current is produced. All that directly I am going to give you. Here, flux is increasing. Anti-clockwise direction. Magnetic field here also towards positive x-axis for the secondary coil. This is now secondary coil. I have taken secondary coil. What's the direction of magnetic field for the secondary coil? Towards positive x-axis. So what is the direction of the original current? Anti-clockwise. But since the flux is increasing, therefore clockwise. Clockwise means what is the direction? Y, X, Z. Y, X, Z. Check the back answer, children. Got it? Y, X, Z. This is how you need to do it. Easier you can do it. Actually, traditional method, what is it? Whenever there is a flux is increasing, Lenz's law states that it opposes the cause of change in magnetic flux. When the flux increases, the secondary coil does not allow it to increase. It opposes. Opposes means magnetic field lines are producing, no, flux is going in this direction. No, it produces the opposite flux in this direction. So clockwise. So instead of doing it like that, I'm giving you induced EMF direction. Okay, using right hand thumb rule. Same way here. Same way here. Tapping the key, just released. When it just released, current decreases, therefore flux decreases. What is the direction of the magnetic field lines? So current is in the anti-clockwise direction. Since the current is in the anti-clockwise direction here. So what is the magnetic field lines here? Magnetic field lines are anti-clockwise towards positive x-axis. Here also positive x-axis. So here also anti-clockwise direction. So therefore X or Y. So current direction is X or Y. Do not change it. Here also anti-clockwise, there also it is anti-clockwise only. So therefore X or Y. Next, this one already we discussed. So therefore flux 5 is equal to BA cos 90. So therefore flux is equal to 0. So therefore no current, no induced current. And the last one, children, this is stretching the loop. Look at the direction of the magnetic field is into. So stretching the loop. Therefore area increases. Hence flux increases. When the flux is increasing, magnetic field is inverse. Clockwise you get. Since the flux is increasing, anti-clockwise. Traditional way of doing, according to Lenz's law, does not allow it to increase the flux. The flux is increasing in this downward direction. Therefore, upward direction, it has to produce a opposite flux. So therefore, anti-clockwise direction. Likewise. So now here same way, compressed. You are compressing the loop. When the loop is compressed, first magnetic field is outwards, area decreases, therefore flux decreases. Hence, induced current anti-clockwise direction should not change it as because flux decreases. Anti-clockwise direction. So anti-clockwise Cbse, Cbse like that. So here anti-clockwise direction Cbad like that. Do you understand, children? Right? Now next, a rectangular loop and a circular loop are moving. It's a $1 million important question. A rectangular loop and a circular loop are moving out of a uniform magnetic field region. Moving out of a uniform magnetic field region to a field-free region with a constant velocity. In which loop do you expect induced EMF to be constant? See, it is ultimately given induced EMF is produced in both the cases. But which loop it is constant during the passage out of the field region? Here, when you are going to move out of the field, what happened? Area enclosed by it is changes. Flux changes because area enclosed by the magnetic field changes. Flux 5 is equal to BA cos 0 because area vector in the magnetic field. How do you find out area vector, children? How do you find out area vector for this? You have to take a rectangle, right? How to find out the area vector for this? If you take a rectangle like that, area vector is upwards or downwards. Either case, what will happen? Magnetic field and the area vector both are in the same direction, therefore flux is maximum. So here flux phi is equal to BA. Induced EMF is equal to minus d phi by dt. That is equal to minus d by dt of flux phi is equal to BA. That is nothing but B is constant. So B, I am taking it out. So L into X, that is L into B. Length into breadth. So that is equal to minus d by dt of this breadth does not change. The length is changing as because you are moving out. So therefore, that is now dl by dt. dl by dt, I'm sorry, here dl by dt into B. So that is equal to minus BV. Okay, got it? Minus BBV with velocity V. That is for the first case, rectangle. That is going to be constant. How do you say it is constant, children? Do you understand what I said? Flux phi is equal to BA cos theta. Area is nothing but B into length into breadth. I mean length into breadth is area. B is nothing but the breadth remains same whenever it is moving. Only the length will be sum of the length of the rectangle will be outwards, right? Outside, no. So therefore the length changes. Therefore I can say dB by dt is nothing but velocity. So BBV, velocity is constant of minus BB into V. But for the second case, so induced EMF is equal to minus d by dt of area of the circle. Area of circle. So that is equal to area of circle, no. Area of the circle minus B into d by dt of area of the circle pi r square. Now you tell me here how to differentiate r square. Minus b into pi into 2r into dr by dt. 2r into dr by dt. So what is 2r into dr by dt? Dr by dt, that is equal to minus b into pi into 2r into velocity. Now here it depends upon what? Radius. It depends upon the radius while it is coming out. So it depends upon the velocity. So therefore, what happens here? This induced EMF will be constant only in the rectangular loop, but not in what loop? Not in circular loop. So which loop you expect? dA by dt is equal to constant for dA by dt is equal to constant for rectangular loop. Rectangular loop. Whereas dA by dt is equal to changing for what loop? Circular loop. Do you get it, children? dA by dt is constant for rectangular loop, whereas changing for circular loop. So hope you understand this, children. The last one, predict the polarity of the capacitor in the situation described. So when the north pole is brought in, we are bringing this north pole here. The polarity attained is also a north pole, so therefore this is anti-clockwise. Since it is anti-clockwise, the current always flow from positive to negative of the battery. So therefore, this will be positive and this will be negative. At the same time, you are bringing it here inside. Since it is inside here, this is also south pole. So south pole clockwise. So therefore, between the plates of the capacitor, the current flows from positive to negative. So A is attaining positive polarity, B is attaining negative polarity. So got it, children? So hope you understand this concept. So learn thoroughly by knowing all these questions. And if you have any problem in understanding, you can just, approach me and then get it clarified. So thank you, children.